Well, hello everyone, my name is Charles van der Walt. I'm joined today by my colleague Vikas Ross. We are both researchers for Orange Cyber Defense, which is the cybersecurity division of Orange Mobile. We greet you today from the beautiful city of Cape Town, which is in South Africa. Please take a moment to follow us on Twitter. Our handle's at the bottom of the page. Vikas knows something about almost everything, and I know Vikas. But we would really appreciate you reaching out and linking up online. So, research is really the story of how we seek answers to questions. And the story we want to tell you about today is how we've been trying to discover the answer to the question, do VPN technologies actually work? And we'll not be talking today about bugs or vulnerabilities in specific technologies, but really examining the question of whether a specific class of technologies provides the kind of protection that we expect in a scenario that we believe is common, used in a way that we believe is common, and from places that we believe is common. And our story has a lot to do with travel. As professionals, and like many of you, Vikas and I spend a lot of time traveling. In fact, if you live as far away from everything as we do, you pretty much have to get on a plane just to get a McDonald's. So we spend a lot of time flying. And if you spend a lot of time flying, like I'm sure many of you do, then you also encounter this a lot. It's free Wi-Fi. In fact, I think we all know how it works. As soon as you get off the plane, first thing you need is a toilet, the next thing you need is a coffee, and then right after that, it's free Wi-Fi. Except, as we know, the public Wi-Fi that we use is almost never actually free. There's always some kind of transaction involved. You either have to pay, I suppose then it's not free, or you have to provide some personal information, or at very least, you need to accept the terms and conditions that this access point demands from you. And so we interact with something that's called a captive portal. We all know what I'm talking about. Captive portal is that web application where you're asked to provide some information about yourself, accept the terms and conditions, perhaps enter some credit card details. But whatever the case is, there's a transaction happening, and it's being facilitated by this technology, the captive portal technology. And the word that I want to focus you on is that word captive, because it really captures a lot of what we'll be talking about today. The captive portal puts you in this kind of weird purgatory state where you're sitting between a space where you've connected to the Wi-Fi LAN, you've got network settings, your machine believes it's connected, but in fact you don't have access to the internet, and you're in this in-between state that we'll be referring to as captured. So bear that in mind as you listen to the rest of our presentation. And it creates all kinds of weird scenarios. So what you're seeing here is a screenshot of a typical Windows machine that has found itself in this captured state between connecting to the Wi-Fi network and being on the internet. And the dialogues you're seeing are all the sort of Windows gadgets and widgets and applications and browser tabs going crazy because they are connecting to a server that's presenting the wrong SSL certificate. And that's happening, of course, because the captive portal has redirected that traffic to itself. It's serving its own certificate, and the applications have recognized that that certificate is not correct. As a sort of curious aside, one of the things that I find relatively amusing is how readily and desperately these applications want you to accept that state by giving you that yes, accept, connect, proceed button. I was particularly amused by Zoom, who make their button big and blue and bold so you can hardly miss it. But also by that VPN provider on the bottom right there, who not only invites you to connect, but also invites you to remember that setting so that you can continue connecting to the wrong VPN server forever without any inconvenience. But this is just one example of the sort of curious state that the captive portal puts us in. This one is a little harder to grasp, but It involves the DHCP settings that are sent by the Wi-Fi AP to your endpoint. And we know what happens with DHCP. It's all the typical things. You get given your IP address, your subnet mask, default routes, DNS servers. But I want to draw your attention to this other setting here also, which is the domain search suffix, option 15, I think. You'll note that what the search suffix is used for is when your machine tries to access a resource on the network via a name that's not fully qualified. In other words, the first part of the DNS name and not the back end of the DNS name. Then this search suffix will be appended to the name that you entered, and that will be used to resolve DNS and provide you with an IP address in the end. And where that becomes problematic is what we'll see in the next example, is when the asset that you're accessing is being accessed by a name which is not qualified. And in this example, what you're seeing is a user connecting to a printer, a corporate printer called Printer HQ. That printer is captured in their config without a fully qualified domain name, in other words, without the end bit. And so what's happening is the stack is adding that DNS search suffix to the end and resolving that. And what ends up happening in this case is that that fully qualified name does get resolved, results in an IP address, which is an entirely different place. In this case, an IP address on the internet. And Vikas will go into this in more detail, but I think you can start to understand why that could be problematic. And what these examples led us to in our story is to start asking the question, what is the role that the VPN technology should play in a scenario like this? Because notionally, it would seem to us that in establishing this, this encrypted and secure tunnel between the end user and the corporate network, what we expect is a kind of a network and security equivalency, where the set of network conditions and security conditions that a user on the Wi-Fi LAN experience should be equivalent to what a user connected to the corporate LAN should experience. That in our mind is notionally the expectation that a VPN creates, and it's that notional expectation that we want to test in our research. And that network and security equivalency is achieved by the VPN by providing three things: it's confidentiality, integrity, and access control. So diving into a little more detail about the research we'll be presenting today, the first thing I need to just touch on very briefly is some of the assumptions that we're working from. And we go into these in a lot more detail on the website that we've created for this research, but just very quickly, we're proceeding from the assumption that working from home via Wi-Fi is common, and under COVID-19, we think that's a safe assumption to make. In normal life, when we were all traveling around, we believe that working via Wi-Fi access points that have captive portals is common. That's a scenario you encounter on a daily basis, and it's growing. We believe that home routers and that kind of home router technology stack is can be expected to be insecure, or at least poorly configured. It's not a technology that we have control over like we have control over our corporate technologies. We believe those kinds of technologies are frequently targeted. We've seen examples of that, Mirai, the Mirai botnet being the most recent example. And we believe that when VPNs are deployed in corporates, it's common practice for those VPNs to use split tunneling, which Vikas will go into in a little bit more detail. I just want to make one more point here, which is that although our story started off by us examining the scenario of the captive portal, it soon became clear to us that there's actually, at a theoretical level, no difference between a captive portal, which is built for that purpose, and a home router Wi-Fi AP that's been compromised and is reconfigured to act in the same way as a captive portal. So when we talk about captive portals and we talk about home routers that have been compromised, we're talking kind of about the same thing. So it's either compromised or malicious Wi-Fi access points. And then given that scenario, we want to argue that there are 6 specific technical threats that we believe a VPN should be able to protect us against. There are obviously other scenarios, but these are the 6 specific scenarios that we identified for our research and which our results will be based on. The first is that we think the VPN should prevent sniffing from happening. An attacker should not be able to glean information on the network about your host because of this tunnel that's supposed to protect us. Secondly, we think the VPN should protect us from sort of DNS meddling attacks, right? When you send out a request for a DNS name to be resolved, the response that you get when you're sitting in that, on that Wi-Fi AP and using the VPN should be the same as the response that you expect to get if you were sitting in the corporate network. And if that's not the same, then we failed on that scenario. Thirdly, we believe the VPN should be protecting us against kind of spoofed websites for phishing, any kind of meddling with a web interface that happens between the user and the corporate network. And again, the litmus test here is equivalency. We're not talking about spoofing sites that occur once users broken out onto the internet. We're talking about scenarios that are possible because the user is in this Wi-Fi state on this Wi-Fi network and not on the VPN. We think there's a very real risk of responder attacks being launched in this scenario, and so we want to test and verify that a user who's connected to this remote LAN is not more susceptible to SMB responder type attacks than a user that's sitting in your private network. We want to test that the interaction with the captive portal doesn't introduce the opportunity for an attacker to inject malicious JavaScript into the browser and therefore repurpose the browser into some sort of attack tool, typically, for example, tunneling via the browser into the corporate network. And then finally, we want to examine the role that IP version 6 plays in this captured state, and we would expect that a host that is on a Wi-Fi network should not be more susceptible to attacks or interaction with its IPv6 stack than a host that's on the corporate network. So those are the 6 specific threat scenarios that we're interested in examining, and those are the scenarios that our tests will be based on. In terms of an approach, we don't have to go into this in too much detail, but basically what we wanted to do was create a standard set of scenarios and a standard set of tests and repeat those tests against a range of significant vendors in this space. We have, at this point that we're recording this video, we've identified Cisco, Pulse, Checkpoint, Fortinet, and Palo Alto Networks. Our goal is to expand that over time. And so again, we would ask you to visit our website. We will be keeping this research updated. And effectively what we want to do is identify standard equivalent configurations across these vendors that we can compare with each other in the context of those 6 threat scenarios that we identified. Once again, here it is, big and bold. Our most current data will be reported on our website. We're recording this sometime before you will be watching it. So if you want the updated information, please take a moment to visit the site. We'll also be sharing other resources, videos, examples, PCAPs, those sorts of things there. You can take a photo of your computer screen. And so finally, before I hand over to Vikas, in terms of summarizing the research question that we're looking to answer today, what we're saying is that if the VPN can be considered the logical extension of the private network to another location, if it's reasonable for us to expect network and security equivalency when the VPN is established, and if we assume that that other location is a Wi-Fi network that's either malicious or compromised, then the question we're trying to answer is how much protection do these enterprise VPN technologies provide against the common and realistic threats that we think we would expect to encounter today. And with that, I'm going to hand over to my colleague, Vikas Ross.
Thank you, Charles. Let's now dive a bit into the technical concepts that's pertinent to this research. Let's start off looking at captive portals. Captive Portal can be described as a very simple piece of setup kit, typically like an access point, router with Wi-Fi, firewall, and maybe a website on it. Now, Charles described scenarios earlier on how you would interact with the Captive Portal. But let's look at it a little bit deeper in a technical context. After your device is connected to the Wi-Fi, you would typically require DHCP configuration or network configuration, and this is provided by the DHCP service hosted on the Captive Portal. The next part is the operating system on your device will try and determine whether or not it has internet access. That internet access test basically requires it resolving a URL and getting a response from it. Before it can get the URL, it needs to have the DNS settings resolved of the host interested in. So it uses basically the DNS server of the Captive Portal to get an IP address. This IP address is now used to do an HTTP request, and this is where the Captive Portal actually starts meddling with this whole process. It effectively intercepts that HTTP request, and it presents a response, an HTTP response back with a status code of 302, meaning temporarily moved somewhere else, and it provides a new location for this website, being the Captive Portal's website. The OS detects that this shenanigans is going on, and it realizes, well, I was testing whether or not we're behind the Captive Portal, so this is probably indicative that we are. It will then launch a browser with which it presents the Captive Portal interface to you as the user on the device. You now have to satisfy the Captive Portal questions, accept terms and conditions, and then if the Captive Portal's happy, allows you internet access. So now your operating system knows it's online, because while you're trying to resolve this Captive Portal state, it literally hammers that same request over and over until it sees, well, connections are being accepted and I'm happy with the response. So let's look at the next concept, which is important, is the DHCP aspect that we encountered earlier in this Captive Portal state. DHCP is important here because that's probably one of the first packets that gets broadcast by your client when it reaches the Captive Portal Wi-Fi. The device on your side asks for a DHCP service to provide it with certain options. At the same time, it divulges some information about itself. The Captive Portal service, DHCP service, responds back saying, oh, by the way, here are the options you're looking for. And this includes important information like your IP address, DNS servers, and here's the more important part that's pertinent for our research, being the domain name and the DNS search suffixes, options 15 and options 119, which Charles alluded to earlier. Those DNS suffixes are important when trying to resolve unqualified domain names. And that we'll see how that plays out a little bit later. Other information provided includes MTUs, routing, etc. It's quite a rich set of options available to us. Next, let's look at VPN tunneling configurations. We will probably see two most pertinent ones, being split tunneling and full tunneling. And I'm going to go out on a limb here saying that split tunneling is probably the most dominant configuration set out there, but it's not the only one. Split tunneling, you're probably all familiar with. Information or packets or traffic directed at the corporate LAN goes over the VPN, and all the other traffic goes directly to the internet. Full tunneling, as it suggests, all the traffic goes to the VPN server on the corporate LAN side, and at that point the policies and routing rules apply as the corporate dictates. So it might even allow internet traffic to be routed back out into the internet. So that's an important concept to understand as well. Next is the role that IPv6 plays in Captive Portals. It's not that common at this stage, but we believe it is becoming more and more common. IPv6 is a very chatty protocol, unlike IPv4. IPv6 relies on neighbor solicitation and router solicitation packets to be broadcasted, and it gathers information that way. So it fills the space where ARP would normally play that role for us. IPv6 can also be configured using DHCP v6, which has the similar type of DNS suffix options available to it. And then there are all sorts of other options also available to us. But IPv6 typically is seldomly considered in security configurations up front. It tends to become a question later down the line. So that's why we included IPv6 as a consideration. Another interesting topic is captive portal lockdown configuration, or sometimes referred to as mitigation mode. These are a set of features or options that is enabled on the VPN client as well as enforced by the VPN server to be able to protect against certain scenarios that we will highlight later down the line. So these are specific sets of configurations to deal with that mode, specifically, which we apply to captive portals as well. Just a comment on when we looked at configuration of captive portals in lockdown mode. Charlie said we looked at 5 vendors, VPN vendors. What was notable, there were 2 of those vendors actually had a reasonable set of lockdown modes up front, and it was clearly documented and clearly visible in its configuration sets. They also included what we call captive portal mini browsers. These are proprietary browsers that is used for when you engage with captive portals. So it is a buffer or a sandbox environment in which a browser is displayed to the user, as opposed to using your default browser on your desktop that might be manipulated in other ways later down the line. 2 other vendors that we looked at didn't have this feature, and they didn't speak directly to lockdown configuration as well, but they allowed you with a very rich set of features that you could configure how you chose to, based on the scenarios you're trying to mitigate. Interestingly, one of the other vendors, VPN vendors, didn't have a IPv6 out-of-the-box mitigation directly for SSL VPNs. It was only applicable when looking at IPsec VPNs. We predominantly looked at SSL VPNs because SSL VPNs tend to be the most compatible when dealing with captive portal environments. Vendor 5 we're still busy testing, so by the time that you reached our website that Charles pointed out, you should see an updated version of configuration or updated findings for this vendor. Now going on to our research and findings. We selected, in this matrix you'll see we selected a set of features, and that's what we refer to as our lockdown features, that we believe speaks to the test cases that you would probably encounter in a malicious captive portal environment. This is by no means a complete set of features, but these were pertinent in our testing, and we feel that they cover the most scenarios that is out there and is applicable. Also, this table it might change by the time that you view the website. At the time of this recording, this was the state of our findings, with one vendor's findings totally outstanding. Next, so let's revisit the question that Charles asked earlier about what do we expect VPNs to do and how do they function. In there, if you recall, Charles mentioned that we expect basically the VPN to allow us to access corporate resources. These corporate resources should basically give us the same type of capabilities as if we were in that LAN environment. So in evaluating that VPN in the environment that we're looking at, we saw 3 categories that we used. In each category, we had certain conditions that we tested for. In the first category, being confidentiality, we looked at whether or not the VPN played any role in mitigating spurious broadcasts of the client. Then we also looked whether or not the VPN played a role in mitigating DHCP settings, specifically DNS search suffix settings that was supplied initially. Thirdly, for that category, we also look if the VPN plays any role in preventing the broadcast or the leakage of sensitive information. Next, under integrity, we determine whether or not the traditional or typical person-in-the-middle style attack applies here, and whether the resilience changes for credential captures or credential theft if VPNs are in play. Lastly, with access control, we looked at whether or not the man in the middle style type of attacks, as well as malicious attackers could use the VPN tunnel to actually get into the corporate LAN via whatever mechanisms they chose. So let's look at the test environment quickly. Our test environment was very basic, very simple. We had a virtual machine that was served on a desktop with VMware, and it had a USB Wi-Fi adapter plugged into it that allowed it to bridge network connectivity to our captive portal. Our captive portal was basically just a simple run-of-the-mill router paired with the Kali Linux environment that played the role of the malicious attacker. And the virtual machine environment hosted our endpoint servers in a cloud environment that we could use for our testing. And that basically simulated our lab environment. Our test approach in this matrix here is important for basically describing the 4 types of scenarios that we tested. So let me describe what you see here. On the left-hand side, you see a column that says captured and online. These are connection states. So in other words, captured state is a very important state that Charles alluded to earlier. This alludes to the fact whether or not we are inside the captive portal state and we don't have internet access. So in other words, you're sitting in a holding pattern almost, and you can only interact with that captive portal and maybe some resources on that network. You do not have internet access. Next, online means that you actually can get onto the internet, which means you satisfied the captive portal state. The standard mode and the lockdown mode is the configuration of the VPN that we actually applied. So which means we have 4 sets of tests that we do, and for each set of configuration and each connection state. So for example, in the captured state with standard mode, basically no internet access, and assuming split tunneling, coming back to saying that we assume split tunneling is a default state, using off-the-shelf configuration. No extra configuration, it was added just what the vendor provided and based on the guidance. So if the VPN vendor or the configuration suggested we should use a different tunneling mechanism, we try to follow that. In the lockdown section, you see we tried the best VPN configuration for captive portal environments, which means that it should speak to the test that we throw at it, and we should be able to see how they respond to that. So that's the best way that we can actually protect the user. Let's look now how our test cases stacked up and what our results was. So this slide here is basically our findings, the TLDR. In a nutshell, there's a lot happening on this slide, but it's basically just taking what we showed you on the previous slide with our findings colored in there. So you'll see in the one quadrant here, the first scenario that I suggested with the captured state, with the standard mode configuration, there's a grid with 6 columns and 6 rows. The columns indicate our test cases, the rows indicate the VPNs that we tested. The red color suggests a state outcome, state or failed, while the green color speaks to a successful outcome. And the gray would indicate we haven't tested that vendor, which this slide might change at the end by the time you visit it. But for now, this is more or less at the time of recording what we found. And in this state, with scenario 1 being the one we highlighted here, basically our initial concern about VPNs contribute almost nothing to actually protecting the user. In the second state, highlighted here with online and still in standard mode, there is some improvement, but not much. So even a careless configuration of your VPN would resemble something like this, even if it's not in a captured state. So not that much better. Looking at a captured state, but with lockdown configuration, we see there's an improvement, but still there are some test conditions in captured state that cannot be mitigated, even though the configuration of those features were enabled. Moving on to the final configuration test set, we see that there is a drastic improvement for an online configuration in lockdown mode. But even with this, the vendors' features and stuff didn't always work consistently as you would expect them to work. But this is an improvement nonetheless. Coming back to Charles' earlier statement about a responder style attack, the column I highlighted there speaks to a test case that we used the responder in to test with. Now, responder is a very well-known, well-understood test scenario involving a tool that mimics certain types of services. For example, it mimics a Windows server with the intention of soliciting a divulging of hashes. It's Intel M v2 hashes, for example. And as you can see, and I highlighted that column for that scenario, it failed. Even in that mode as well, it failed, and it marginally started improving as we go to stricter configuration, but also as we move from captured into an online state. So let's see how this actually looks when we apply this in an environment. Looking at the demo videos, as Charlie alluded, will be available on the website in the URL that we provide. So we'll just look now at some screen captures. Here you'll see a VPN client that realizes it is behind a captive portal. It indicates that also by popping up the captive portal mini browser, highlighted here, and it resembles a web browser to some degree, but this is purely a proprietary interface for that specific VPN. Next, we highlight the fact that the DNS cache is still active. The DNS cache is not flushed, and it's probably still resolving in the background, which means we can speak to a DNS server, most likely the captive portal. Here we enact the actual test to see whether or not we can solicit a DNS responder attack by doing a connection attempt to an unqualified UNC path highlighted here, which means that it should try and connect and find a connection. In the Wireshark trace, what we show there is actually, if you notice that the unqualified hostname now all of a sudden have a fully qualified hostname. And that's important to realize that all of a sudden a domain name now appears as part of that hostname. Where did it get that from? Remember our option 15 and option 119 that we spoke about? Basically, the DHCP settings of the VPN provider, as well as the DHCP settings of the captive portal, provided these options. And it is injected in the configuration. And now our host is trying to say, well, does anybody know who this host with this suffix is? And it try and iterates until it gets an IP resolve, and then if it resolves, it actually just connects to that. And this is where the DNS suffix plays a role in actually allowing us to solicit unwanted or solicit traffic. So coming back to that, you can see the same attack or same test repeated with the Wireshark trace in the background showing actually a successful connection established to our responder. And here's the responder window with the Intel M v2 hash captured. Now let's look at this attack in a lockdown mode while the VPN is connected. So we're going to basically have the same attack play out. This stage you can see the VPN realizes it's connected to the internet. It has established its VPN. VPN is running. Full lockdown mode should now be engaged. But when we run our test, trying to do the same unqualified UNC path connection, we see that in the background of Wireshark, it actually successfully establishes a connection with our responder, and the same scenario played out. Some observations. In dealing with these VPN configurations, I realized I'm dealing with quite a complex set of features. There's overwhelming number of knobs and bobs that you have to tweak to get some of these things to behave in the way that you wanted to do, especially in this type of test cases that we set up. That was quite overwhelming. Also, it speaks to the fact that training matters, experience matters, as well as support from your vendors that you engage with. That ultimately qualifies selecting your vendors matters as well. Another comment on captive portal mini browsers, they tend to be inconsistent in their behavior. That might give a problem or might have a user experience problem for non-technical users. That might be presented, in my case, I've seen the default browser pop up before the captive portal mini browser pop up, and that can cause confusion. Another comment on mobile devices that we just tested to see how they interact with captive portals in a similar way. We noticed that captive portals behavior inside mobile operating systems are a lot more natural, well taken care of. It feels more baked into it. So there's a lot to be said about the desktop environments that we find ourselves in and how that speaks to captive portals. Thank you very much, Joel.
Awesome, thanks Vickers. So it's for me to try and wrap this up for us. I need to take a few more minutes of your time. If we summarize what we're saying, said a lot, but if we summarize it, basically we're arguing that we believe that there is a realistic and common set of conditions, or it's a common scenario where users are working from either compromised or malicious Wi-Fi access points. And we think that scenario needs a place in the corporate threat model. Captive portal is common, as we've argued, and we think it's becoming more common. But to be clear, captive portal represents an example of this state, of this captured state. It's not a prerequisite for the set of problems that we're talking about. And then I think what's really important is we're arguing that we believe that this expectation of network and security equivalency that we spoke about, which is supposed to be provided by the VPN, we think that's realistic. And so we think that there's a realistic expectation that the VPN should protect us against the threats that we outlined. And then if I just draw your attention again to this to this table that Vickers shared with us, the first thing you've got to take away from this is in that top left quadrant where you see all of that red. That's the VPN not protecting you against any of the threats that we outlined for any of the vendors that we tested for. And of course, it's perhaps not reasonable that the VPN can protect you at that point because it's not connected. But the point is there is an expectation of equivalency, and that expectation is fundamentally not being met. And then as Vickers pointed out, as we traverse through those four quadrants from top left to bottom left and then up to top right and then down to bottom right, what you see is that there's less and less red and more green. So we are experiencing higher levels of security, but at no point do all the vendors protect us against all of the tests. Even right down to that bottom right-hand quadrant where we're in lockdown mode. In other words, all the appropriate features have been put in place and the VPN is established. Even at that point, there are still some of these threats that we're not being protected against. So the effectiveness of these offerings varies substantially and frankly quite erratically across the different vendors. What do we do about that? Well, I think there's some basic technical things that should be quite obvious by now, so I'm not going to spend too much time on them. Firstly, you've got to understand and you've got to use these lockdown features. And I'm not saying that's easy or that your users are going to like it, but understand that without those lockdown features enabled, things are looking pretty bleak for you in terms of the protections that we think you're probably expecting. In doing that, you've got to make sure that you control and centralize DNS. A lot of these attacks pivot on our ability to manipulate DNS. And if you can prevent that from happening, then you're looking much better. In doing that, you want to make sure that you're fully qualifying your internal DNS names. Again, domain search suffix poisoning is not essential to this, but it's certainly a very easy way to enact some of these threats. So if you can fully qualify your internal domain names, that's going to make your life better. You want to avoid split tunneling if you can. I know there's a resource constraint, but certainly, and we will publish a version of this chart where we have full tunneling enabled in all cases, and you'll see it looks a lot better than when you're using split tunneling. You want to be careful of session timeouts. One of the things that we noticed, which is quite curious, is that if you allow your VPN session to time out, say every 24 hours, then you end up in a state where the user's got his laptop connected to the Wi-Fi, goes to sleep or goes to the toilet, comes back, and the session is timed out, and it all drops into the clear again. So I'm not sure why VPN sessions time out, but they shouldn't. And then finally, I think what should be apparent is that you want, in addition to your VPN, you want to have some kind of EDP, EDPR, firewall, something that's not only protecting you against inbound traffic, but it's also preventing data from leaving the machine, particularly that like 445 outbound is a big problem. At a slightly higher level, tactically, what's clear here is that we need to understand and remap the threats that we're facing to the technologies that we're using. It's a complex jigsaw, and Vickers spoke about how nuanced and how many knobs and bobs there were in that VPN configuration. Each of those knobs and bobs has a specific impact on what element of the threat model is being addressed. So you need to understand that. You probably want to engage with your vendors to help you with that, because the level of complexity is quite overwhelming. And you probably need to think carefully about your vendor choices also, because as we said, the behavior varied quite a lot. And so you're probably going to want to look at this almost at a feature by feature level to determine which vendor is going to give you the right mix of features for what you understand your threat model to be. And I'll go into this in my next and final slide, but we really think that what this illustrates is that perhaps it's time to revisit the paradigms that we're applying here. And maybe there's fundamentally different ways to think about this problem. Like instead of trying to protect our users on the free Wi-Fi, maybe we just get them to avoid free Wi-Fi completely. And instead of trying to force them into this tunnel and bring them into the corporate network, maybe we leave them out of the corporate network and just use kind of basic controls like SSL, certificate pinning, and strong authentication to facilitate access to the resources they need. If we can get rid of Active Directory and all of those Microsoft protocols, when the user's not on the network, again, a lot of this stuff goes away. And of course, that leads towards the whole discussion around zero trust, which is a much bigger topic for us to discuss today. I do want to sort of claim my time, or claim the privilege of just kind of reflecting on this at a slightly higher level, maybe a little philosophically, before we're done. It occurs to me that the whole notion of free Wi-Fi emerged and has become popular because businesses see it as a way to attract clients. You've got to be able to give your clients free Wi-Fi, otherwise, they're not going to come and drink your coffee. And as that grew, what emerged was these legal and liability concerns. If somebody's using my Wi-Fi, am I responsible for them if they do something bad? Who are the police going to ask, etc. And so what the lawyers did is they insisted that there be some kind of transaction between the Wi-Fi provider and the user. And how that was enforced was via this idea of a captive portal, which is actually a relatively new idea. I think the RFC dates back to 2015. So the captive portal was put in place to formalize the transaction between the user and the provider. Once the captive portal is there, of course, the business has other ways to monetize that transaction now by collecting your data exhaust, your behavioral data, or selling you ads, or whatever the case may be. But it's driven by business requirements of the provider, not by user requirements. And it creates this awkward state, this purgatory, this technical purgatory that we spoke about. And so what happens is the VPN providers who are really used to dealing with the previous version of the internet now have to pivot to deal with this new reality where you sit in Wi-Fi purgatory. And they do that by implementing all of these highly complex, nuanced, technical features, which our research shows really don't work because fundamentally the odds are stacked against them. In that state where the machine is captured on the Wi-Fi network but can't talk to the internet, the VPN technology really just can't do anything. And so we stand here today saying to you, well, actually what you need is more technology. You need to add EDP or EDR or firewalls or whatever to protect you in that scenario. And so this sort of cycle continues. But really what's happening is we have a struggle between two business models. There's the business that wants to provide you free Wi-Fi because respectfully it serves them. And then you have the businesses that want to sell you protections because that's what they do. And you're kind of stuck between the two. And it occurs to us that if all you did was take the free Wi-Fi out, then all of these other things would also just disappear. And so I think this kind of speaks to the point of maybe readjusting our paradigms a little bit and asking ourselves the question, is free Wi-Fi really free, I guess? And then finally, on a closing note, I just want to take 1 minute to say thank you very much to the vendors that supported us. All of the VPN vendors have been engaging with us, have been assisting us in numerous ways. But I also want to give a particular shout out to the team at Finite State, They're an IoT vulnerability assessment company that assisted us in analyzing almost 800 VPN firmwares to try and understand some of the things that we're looking for. They have a remarkable data set and a remarkable technology, and we just wanted to say thanks to them and encourage you to go have a look at what they're doing. And with that, we're out of time. All that's left for us is to say baie-dankie, which is Afrikaans for thank you, and we look forward to hearing your questions.
Hi everyone, thanks for joining us tonight. We have just 1 minute, I think, for questions. So if there's anyone with a question or comment, then shoot, and I'll make Wikus answer. No? Comments? All right, well, let me just leave it to say, as we said numerous times, the updated findings are on the website. We're continuing to test with the 5th vendor, and we hope to add more. So visit us there from time to time. Also, I've updated the white paper with a copy of that summary table. So if you download the white paper, you should expect to see that summary table right front and center, sort of near the top of the paper.
Correct. And to answer Daniel's question there or statement, it is important to combine different solutions, because, I mean, to be fair, VPNs aren't a single solution for everything, and they address a specific need which has grown out of a long history of requirements built up over time. So I think VPNs alone can't do the job, and it's a good indication as well that we need to combine our efforts and understand our threat landscape, that we know how to address these things. Any more questions? If there's no more questions, then thank you.
Doesn't look like it. Thank you very much for everyone. Visit our website, follow us on Twitter, and we'll speak to you soon.